Okay, now the Bernoulli's principle. Before we go any further, I would like to talk about something before we enter the Bernoulli's principle. So the first thing we need to understand is a streamlined flow. What is a streamlined flow? A streamlined flow. Okay, now let's say that we have a fluid flowing. Like, how do you make a fluid flow? Let's say this is water in a tube, So if you want to make it flow, we would apply pressure. Okay, we would apply pressure here. We apply pressure here, and then that pressure will cause the water to flow from here to here. There are many methods you can make it flow. Actually, you can make it like sloping. Okay, so with the aid of gravity, you can make water flows. Or I can just put a pump here, a pump that creates the pressure to push the water flowing in the tube. All right. So there are many methods that you can make it flow, but here we'll focus on the making fluid flow using pressures. Okay, so first thing to understand is what causes liquid or fluid to flow. It is pressure that causes liquid to flow. Okay, you must have a pressure applied on one side, and then there's another pressure here which is lower than this one here. So water will flow from high pressure to low pressure. Okay, it is always high pressure to low pressure. It cannot flow from low pressure to high pressure. Right. Now, in a streamlined flow, you may have seen some of the videos where like the tap water flowing, and then you can see very smooth, as if the water wasn't flowing at all. It's like very smooth that you couldn't see that the water is flowing. It's like as if the water is staying still, right? That is an example of streamlined flow. Okay, you have seen video where you may have seen video where like they open the hydraulic oil. Okay, they open the tap where the hydraulic oil flows out, and then the flow of the hydraulic oil is very smooth. It's very smooth that you couldn't see that it's moving. Okay, it looks like as if everything is just at rest like that. Okay, so that is one example of a streamlined flow. So what happened in a streamlined flow is that, now let's say that we have 5 particles. I will make here 1, 2, 3, 4, 5. Okay, we have 5 water molecules flowing in one direction here. After a certain period of time, right, the order of the particle is still the same. That means after a certain period of time where it is flowing, particle here remain in this order, 1, 2, 3, 4, 5 here. Okay, so every second, the order of the particle always remain in the same position. Now, if I compare with another type of flow, which we call turbulent flow. Turbulent flow. Here we have 5 particles. 1, 2, 3, 4, 5. After a certain period of time, you will see that the order will change. That means some particles have higher speed than the other. In the streamlined flow, right, all of the particles, they have the same speed. But in the turbulent flow, some particles, they may flow faster than the other. So let's say particle 1 flow faster. So particle 1 will jump over particle 2. It will kind of take over particle 2. Same here, this particle, okay, may be traveling faster. So it will take over this one like this. So that means after a certain period of time, you will see that the particle order of arrangement has changed. So here, the 2 is here, and then 1 has overtaken this one. Then we have 3, 5, 4, like this. Okay, so this is different from here in terms of the order of the particle. Here, particle tend to overtake, like one driver overtake the other driver, right? Now, when you want to overtake, right? Let's say you want to overtake the car in front. What do? You have to side to the next lane, right? The other lane, and you have to overtake it. So that means you need room to overtake. Same as what happened here. If the particle wants to overtake the particle in front, it needs extra room to overtake it. That means it has to move to the side, okay? It has to move to the side and then go to the front. So the action of the particle moving to the side and then overtake the particle in front creates an extra push to the side wall. Imagine that this water is flowing in a tube, okay? Imagine that this water is flowing in a tube. So you have a tube here. And then the action of the overtake, when this particle tries to overtake this one, it will push against the wall. It will push against the side wall, right? Because it needs room to overtake, right? So it needs room to overtake, it will move to the side and it pushes the wall here. This action will create an extra pressure on the wall of the tube, on the side wall of the tube, right? And same here, this particle will push. So there are a lot of push on the side, on the bottom, on the upper region of the tube, right? So as a result, the turbulent flow creates extra pressure. This one will create extra pressure in the tube. Okay, and then the nature of the flow is that it will not be in order. Not in, okay, yeah, put it here, not in order. What about the speed of the particle? The particle speed varies from one molecule to another molecules. Okay, so turbulent flow. Now, what about streamline flow? Streamline flow is the one that is very smooth, right? So every single particle, they have the same speed. They have the same speed, and then they are flowing in a very orderly manner, okay? They are all in order, like this. One will not overtake. This one first, this one, this one. After a few seconds, then it will still remain like this. So that is the difference in the nature of the flow. In general, we got two types, so streamline and turbulent. Now, in this lesson, in the Bernoulli's principle, we will focus on only the streamline flow. Okay, only what? On the streamline flow. So in the streamline flow, there's very important principle. What principle is that one? We call that principle the continuity of motion. Here I write continuity of motion. Now, what is this thing? This is very important principle in the streamline flow, and that is also related to the Bernoulli's principle. So the continuity of motion says like this. Suppose that I have a tube. Okay, my tube goes like this. At the bottom region is, okay, horizontal. And then here we have a bigger cross section. And then we have a constricted area in the middle. Okay, now suppose that the liquid in the tube is flowing in streamlined manner. Okay, so that means one will not overtake the other. If I want to describe, if I want to draw to show the liquid flow, then I will draw what we call as streamlines. So it's kind of like a line representing the flow of water. So if I want to draw here, the streamline, the way we draw it, it has to be a continuous line like this. This is the first one. So let's say I draw the second one. continuous line like this, and then one more line here like this. Okay, now we got 3 streamlines here. The streamline number 1, streamline number 2, streamline number 3. We can see that before going through this channel, there are 3 streamlines. In the middle of the channel, inside here, there are also 3 streamlines, and outside there are also 3 streamlines, and one streamline cannot cross the other one. It's like this. This is the streamline upper one. The bottom one cannot come to the top like this. It doesn't overtake like this, right? Okay, so the streamline, they go like this. Okay, like a very orderly manner. This one cannot suddenly jump over or cross the other streamline. And we can see the line does not intersect. They do not intersect. This is how we show that it is a streamlined flow. Okay, right. Now, looking from here, if I say in 1 second, I compare these 3 sections, here, here, and here. In 1 second, I send 10 liters of water. 10 liters of water going in here. So you have 10 liters of water coming in. Then, how much do you think is the water coming out of here in 1 second? In 1 second, I send in 10 liters. Same as over here. In 1 second, there will be 10 liters coming out. Why 10 liters? Because how much I send in, how much I get out of it, right? Of course, the tube cannot produce any water. Okay, now I see the line is a bit unstable. Let's have a few second break and let me check the line again. Just a second, guys. Because I can see there's this pop-up saying that internet connection is not stable. Okay, now it's good. Now it's good. It's back. Okay, I'll repeat a bit. Just now I was saying that here in 1 second, I send 10 liters of water into the tube. How much water I get out of here in 1 second? It will be the same 10 liters also, right? Because how much I send in, how much I get out of it. So here 1 second, I will also get 10 liters. So if I ask in the middle, how much water is flowing in 1 second across the middle? This will also be 1 second, 10 liters, right? 10 liter, 10 liter, 10 liters. Okay, so that tells us the same quantity of liquid flow at every cross section. I will write it here. That is one very important point. Same quantity of liquid flows at every cross section. Okay, that is the nature of the flow. Now, here, if I say I want to calculate what is the volume flow rate? What is the what? Volume flow rate. Here, volume flow rate. That means how much volume. We are talking about quantity. Quantity is talking about volume of water. Okay, how much volume of water? I want to know how much volume of water is flowing in every second. That is, we call volume flow rate. Okay, so flow rate means per second. Volume per second. Okay, so how much volume per second? Here, I will make a quantity. Suppose that our tube is like this, having a cross-sectional area of this one and a length of x. Suppose that this is our tube. Water is flowing in the tube in 1 second. Okay, so imagine that there are water flowing in the tube in 1 second. So let's take this as 1 second. Now, water flow from here starting 0 second and it flows to a length of x in 1 second. So if I want to get the volume flow rate, I will get the area here, the cross-sectional area times into the length x, right? That I get the volume. So volume is AX. That's the V. Volume of water flowing is AX, right? So in 1 second, that means in 1 second, it goes like this. This one I will divide by time, which is 1 second. What do I see here? What do I get here? AX over T, right? And then we can see that this X over T, which is distance, divided by time, we get velocity. So AV is the volume of water flowing per 1 second. Okay, so this I will call my volume flow rate. Okay, volume flow rate, which is equals to A times into V, like this. So amount of water flowing every second is the same. Same quantity, right? Same quantity. So that means the volume flow rate at each section must be the same. And again, that is very important takeaway. So the volume flow rate across the tunnel, across the tube, whatever you want to call it, is the same. I will write it here, volume flow rate. Okay, volume flow rate across the tube, across the tunnel is the same. Okay, so that means I can write AV, right, is my volume flow rate. Here, A1, V1. Over here, if I look at this section here, I can call this A2, V2. The volume flow rate here must be the same as the volume flow rate here. A1, V1 must be equal to A2, V2. And the volume flow rate here, A3, V3, must be equal to here, must be equal to here. Okay, so according to the continuity of motion, the principle of continuity, it says what? Okay, one key point. It says the volume flow rate at every cross section must be the same. So I can write this as A1 V1 equals to A2 V2 equals to A3 V3. Okay, now what does this tell us? Why we want to know this? What is important about this? Okay, see, when the area decreases, what happened to the V? You know that you know that this has to be the same, right? This has to be the same as this. So if we compare two positions, I compare here and I compare here. This one has a bigger area over here. That's the area. This one has a smaller area. Since that these two has to be the same, so if area number 2 is smaller, what does it mean in terms of the velocity? The velocity will be higher because it has to be the same as this one. Whatever the quantity here, if this is 100, If area decrease to 10, the velocity has to be 10, 10, 10, 100. If area decrease to 5, then the velocity has to be 20. 20, so this one into this one, we get 100, always equal. So that tells us what? That tells us if the area decrease, then our velocity will increase. Velocity of what? Whose velocity is that one? It is the velocity of the flow of water at this here. Okay, so according to what? According to the principle of continuity of motion, it says that whenever the cross-sectional area is small, the velocity of the flow will increase. Okay, again, whenever the cross-sectional area is small, the velocity of the flow will increase because the mass or the volume flow rate must be constant always. So the way you think about this, okay, logically, you can also think about this like this. This is big area, right? So big area, if you want to pass 10 liters of water, you can do it slowly because the area is very big. If you want to pass 10 liters of water across it, you can do it very slow, right? Because one time is very huge volume, right? But in this middle section, if you want to pass 10 liters of water across the smaller section here, okay, then you have to pass it very fast because each time you pass the water, it is just a small volume, right? So you have to do it very quickly. That means the velocity here will increase very fast. Okay, so that is how the flow behaves in a tube. In a tube, so let's say at like this, the flow, the water come here at first, right? It's very slow, V1. It goes very slow, and then suddenly it goes through this one, V2. It goes very fast. It goes very fast, and then coming up here, it comes back very slow. So the velocity at here and here is the same, but the velocity here is it increases. This one, the action you see everywhere. Ever stand in a hallway, and then you will feel like it's very windy. Okay, you will feel like the wind is very, okay, the speed of the, because the wind, the air is also fluid, right? Not only water, air is also fluid. So that means air also flow faster in all this narrow hallway. Okay, you may have noticed this one in all the narrow hallway, or maybe you just simply close the door, and then this narrow hallway, you can feel like it's very, the wind speed is very fast. It's because of this principle here. Okay, principle of continuity of motion. Okay, so here we will make a conclusion. Here we say what? When cross-sectional area is small, velocity of flow increases, and vice versa. Okay, when cross-sectional area is small, velocity of flow increases, and this we will use it in our Bernoulli's later. Right? So let me give you another example like this. If I go to a river, let's say I go to a river, and then I want to see which part of the river is deep region and which part of the river is a shallow region. How do I determine that one? Let's say I go to a river and then I see, okay, this is the river, the bottom of the river. Okay, this is the bottom of the river. So it goes like this, and then like this. This is the bottom of the river, and this is the river up here. I cannot see. I'm standing above, outside the surface of the river. I cannot see what's underneath here. I can only see that the water is flowing up here. Here it is flowing at a certain velocity V1. Here it is flowing at a certain velocity V2, and here V3. Now, judging from the speed here, I can tell how deep is this one without seeing this. How do I tell? Again, it's based on the continuity of motion. When velocity is high, what happened here? A1, V1 equals to A2, V2. If the speed of the flow I see is very high, that means what? That means the cross-sectional area is very low. But where is the cross-sectional area here? The cross-sectional area, you can think of it as the depth of the river. So if I take the depth of the river, here I take this depth. This may be the cross-sectional area. What is the cross-sectional area here? The depth of the water. This is the cross-sectional area, A2, A1, and this is the cross-sectional area, A3. If you see that V1, the water flow very fast, what does it mean? That means A1 is very small. That means here, comparing these two, which velocity will be faster? I will make an adjustment here. Velocity V2 will be larger than V1. V2 will be larger than V1. Why? Because A2 is shallower than A1. Okay? Because we know that when V2 is large, A2 must be small. Right? When V2 is large, this area must be small. So that tells us, judging from the speed of the flow, that tells us how deep is the water at that region. Shallow region, this shallow region will have faster speed of water. Speed faster, speed higher. In the deep region, like this one, here area is very big. So if area is very big, A3 very big, then what happens to V3? V3 become very small. So here velocity flows very, very slow here. This is deeper region. Like this. Okay, so that means if you see the river water flow very slow, very calm, that means the depth is very huge. It is very deep. Okay, so if the water flow very fast, then you know that that is a shallower region. So deep water, deeper region always has calm water. Deeper region always has calm water flowing. Okay, the flow of water is calm. So that is also one example based on, what is this? Continuity of motion. What is the conclusion that we get out of here? When cross-sectional area is small, velocity of flow increases. This one, you have to remember this one, okay? Now, let's look at next part. Erase this. Yeah, now let's continue. So now suppose that we have a tube. I will make a tube like this. This tube is cut out to make 3 columns, such that the water can rise in this column. Initially, I close the tube, okay? I seal the tube such that no water can flow in and no water can flow out. And then I fill this with water. At first, I noticed that the water column is at the same level. Why should it be at the same level? You have learned from liquid pressure. Pressure is the same at the same level, right? So if I draw a line here, they're all having the same height, h. That proves us the pressure at the bottom. Here we'll take 3 points. I will call this x, point y, and then point z. If I compare the pressure at these 3 points, the pressure at x, y, z, they are all equal. Because the height of the liquid is the same. If one side is larger than the other, let's say if this is larger, then what happens is that it will push the water higher. Okay, if the pressure here is larger than the pressure here and here, then the water will be pushed higher. So since the pressure here, here, and here are equal, then the height will be the same. Now, keep in mind that this one, the water is not moving. The water is not flowing. The water is still stationary. Okay, no motion. So we can conclude that judging from the height, I can say that pressure at x is equals to pressure at y, and it is equals to pressure at z. Okay, same pressure. Now, suppose that I open the valve. Okay, I open this two valve. Let's say that this is connected to a pipe. Okay, this is connected to a pipe where you have a supply of water here. Supply. If I remove the valve, can you see this one? Okay, this one is supply. I put supply of water here. Now, let's say I remove the valve. When I remove the valve, right, then the water will start flowing from here down, and then water will continue to flow to this direction. When there's water flow, let's analyze the pressure. Remember at first, at the start of the lesson, I mentioned that I apply pressure here, so the water will flow from high pressure to low pressure region. If I apply pressure on both sides, if I put a pump, I put two pumps, I put two pumps at both sides like this. Can the water flow? You pump water here, you pump water here, the water cannot flow, right? So water will be at still like this. If I apply pump at two sides, that means if the pressure is the same at both sides, there will be no flow of water. Only if I remove the pump here, there's one pump here, then there will be a pressure difference. Higher pressure, lower pressure, water will flow here. Same here. If I say that the water is flowing from here to here, then where is higher pressure region? From here to here, where is higher pressure region? This here is higher pressure, here is lower pressure, because water flow from high pressure region to low pressure region. Okay, so if I compare the pressure Px, I will find that Px pressure is greater than Py and is greater than Pz. Okay, why is the case? Because I know that water flows from higher region. Higher should be higher pressure region. Higher pressure region to lower pressure region. Like this. High pressure region to low pressure region. So the flow is moving like this. Left to right, left to right. So now, if this pressure is highest, followed by Py and Pz, Then what does it mean in terms of the height? How does it affect the height here? This pressure is the highest, right? So that means if you have high pressure here, then the pressure will push the water higher. Okay, high pressure will push the water higher here. So that means what we see is that the height of the column of the water will be highest in the first column. So I will change this height. This one will become like this. What you will see, what you will notice is that this water will be the highest, followed by what? Followed by the second one. Py is lower pressure, so this has to be lower. And then Pz is the lowest pressure, right? So this has to be the lowest, like this. Okay? So this is what we see. This is H, X, Hy, Hz. Okay? So this is the reason why. If you're asked why should the height be different, why the height is different here? Because the pressure is not the same, because water flow from higher pressure region to lower pressure region. So the higher pressure region will push the water higher. Okay? Now, why cannot it keep on going higher? Because from there it is balanced by atmospheric, right? You have atmospheric down here. P atm, P atm, P atm. Like this. Okay? So from there they find a balance. Okay. This is without the Venturi effect. Without Venturi effect. What is Venturi? Venturi is like a narrow tube like this one. If I make the water tube constricted, okay? If I make the water tube here constricted, this tube, I will call it a Venturi tube. So is this a Venturi tube? This is not a Venturi tube. The cross section is the same. So I would say that this is without the Venturi effect. Now let's see what happened with the Venturi effect. Okay, if I use a Venturi tube. Now I will make my water tunnel like this. I will make my water tunnel become like this. At first cross-sectional, and then it constricted here, and then increase again, such that the area cross-sectional on the left and the right side are the same, but the middle section are constricted. Okay. Is this diagrams? Okay, let me redraw it. Make it straight a bit. Okay, like this, So this is a Venturi, we call it what? Venturi tube. Okay, Venturi tube. Now, in the Venturi tube, I make the water flow from here. Water start flowing from here. Now, I make 3 columns just like the previous one. I make 1 column here, 1 column here, and 1 column here. And then I see when the water flow, what is the height of the water at each of the column. Now, see, water flowing from here, water flowing here, and water flowing out. We separate this into 3 sections. So we got the water flowing here, V1, water flowing here, V2, water flowing here, V3. Where is the highest speed of water flow? You have seen this. You have learned continuity of motion. When cross-sectional area is small, velocity of flow increases. Where is the smallest cross-sectional area? V2 has the smallest cross-sectional area. So that means V2 will be the largest. Because area is the smallest, so V2 is the largest. That means the speed of the flow, at first it flows steady at a certain speed, and then suddenly increase, and then come out from here, it flows steady again. At first it's steady, increase, and then reduce steady. The speed here must be the same as this one here. V1 is equals to V3. Okay, V1 equals to V3. But V2 is larger. V2 is larger than this one and this one. Now, according to Bernoulli's principle, what do you know about Bernoulli's principle? Bernoulli's principle says that the faster the flow of the fluid, when fluid flow, when the speed of flow increases, what happened to the pressure? The pressure decreases. That is what Bernoulli's principle is saying. When the speed of flow increases, the pressure decreases. The Bernoulli's principle relates between speed and pressure. The continuity of motion relates between area and speed. Okay, so that means if I change the area, I affect the speed and I affect the pressure. Okay, so V2 is the largest. What happened to the pressure? If the speed flow is fast, increases, the pressure decreases. That means P2 will have the lowest pressure. P2 is lowest. Because the speed increases, the speed is the fastest. Okay, speed is the fastest, pressure is the lowest. Now, what about here and here? This one and this one, from here, water flow from higher pressure. Now, the speed, first of all, the speed are the same, right? The speed are the same. That means they should have the same pressure, right? Speed are the same. But remember, water flow from higher pressure to lower pressure. That means, are these two the same? No, this one will be slightly higher than this one here. Okay, because water flow from higher pressure region to a lower pressure. So P1 will be slightly higher than P3. If I want to arrange the pressure in biggest to smallest, I will put P1 here is the biggest. P1 biggest, followed by what? P3. P3. And then P2 comes the last. That is the lowest pressure. P1 bigger than P3, bigger than P2. Here. Can? What is the pressure here? The pressure at this point, just below the column. Okay? The pressure I'm referring to, the pressure at this point, just below the column, and this pressure is pressure at this point, just below the column. At that spot. Okay? So now P1, if P1 is the greatest, that means it will push the liquid the highest. Right? It will push the liquid the highest. Okay, whatever height here. H1. Come second, P3 is the second one. So it will push the liquid high, but not higher than this one. If this is here, this would be smaller than that one. Like this. Okay, this is H3. Last is P2. P2 is lowest. That means the water level should be the lowest among all of this. Here I will put here. This is H2. Lowest. So what you notice is that the water level is different in height. Why is this the case? It's because of the pressure here, pressure here, pressure here. So this effect, what we see here, the effect of the pressure. The middle one, where the speed flow the fastest, always has the lowest height of water. This, we call it the Venturi effect. Okay, Venturi effect. Under Venturi effect, where you see the tube is constricted, is narrow at one end, okay, and then the pressure is affected. This is Venturi effect. This one has no Venturi effect. So without Venturi effect, you will also see that the pressure different here because water flow from high pressure to low pressure region. Okay, so such question is very typical questions that will always be asked. So take note for this one. Now, next one, we will look at, based on the Bernoulli's principle, how does aircraft fly? From where we get the lift on the wings of the aircraft. Here, we know that the wings of the aircraft creates the lift, and that lift is used to lift the entire aircraft. But how does the lift is created at the wings? Based on Bernoulli's principles, okay? We will see how does it work. Give me 1 second. Okay. All right, let's continue. Yeah. Here from this diagram, I have a aircraft wing. How is this diagram? Like, how do we relate to this diagram? Okay, this is the aircraft wing. This is the aircraft body. Okay, it's too big already. Okay, doesn't matter. This is the aircraft body, and here's the aircraft wing, like this. Okay, so this is the wing, this is the body. So the aircraft is going like this towards you. Okay, going like this. Now, if I look at the wing from the side, I look at the wing here, then I will see this diagram. Okay, again, here's the aircraft. That's the aircraft wing. Huh? So the aircraft goes like this towards you. And if I see the wing from the side like this part of the wing, I cut the wing, and then I see from the side, this is what I see. Okay, that diagram on the board. So this is the side of the wing. So like this, the aircraft goes like this. I'm seeing the side of the wing like this. Now, we look at how does the aircraft generate the lift that is used to lift the entire plane up. Okay, now here we will draw a streamlined flow. Imagine that this thing is moving, all right? So it's moving in one direction, it's moving to the left. As this wing is moving, it is cutting through this huge pocket of air. So as the wing is moving, imagine that this huge pocket of air, and then you have this tiny wing is moving inside. This wing is cutting through the air. This wing is cutting through the air. So the air goes like this, and then it cuts the air like this, and then once it moves away, then the air comes back like this. Right? So you can imagine that this is a huge pocket of air where something very tiny is moving in this huge layer of air. So as it goes, it cuts through the air like this, and then like this. All right? So if I want to draw the air, I want to draw how the air flow over the aircraft wing. Then it looks like this. This is the air. I will draw streamlines, just like how we did previously, right? How we did. So I draw streamlines. This is the second streamline. The third streamline goes like this. And then we have this, like this. Okay? What is this? Line number 1, line number 2, line number 3, line number 4. These are the wind. Think of it as a particle, okay? The particle goes over like this. This is cutting through the air. So according to streamline, what you learn about streamline, they do not overtake, right? This layer is this layer, this layer is this layer. One layer, the layer at bottom cannot overtake the layer above like this. They flow very, very smooth and very ordered manner like this, just like what happened here. So streamline 1 will remain here, 2, 3, 4. Okay, now this particle down here, imagine you have particle down here. This particle flow across this distance. Which distance? The distance at the bottom here, all over to here. Comparing another particle that goes here, above the surface. Now, the particle here go above the surface. This particle here travel a longer distance. If I compare two particles, particle A and particle B, particle A is the one that goes above it. The curvature here, particle B goes here. If I say that they have to reach the end the same time, these two particles have to come here at the same time. Just like the air cut through, right? The air cut through, and then the air have to come the same time. If they want to come the same time, then which particle travel faster? V equals to distance over time. If the time is the same, okay, they have to reach the same time, and whoever covered the longer distance increase, will travel faster. Whoever travel longer distance will travel faster, provided the time is the same. So that means particle A will travel faster than particle B because it has more distance to cover, like this. Okay, if I want to see how this in effect, like this, when this move like this. Like this. Okay, again, this one move very slowly, this one move relatively faster, like this. Like this. Okay, the particle above will travel faster. Now, if the particle above travel faster, that means the VA is higher, VA, and VB. VA is higher than VB. So what happened here? If VA is higher than VB, then what about pressure? The pressure at A, according to Bernoulli's, again, when the speed of flow increases, the pressure decreases. So that means we are looking at two regions. We are looking at the first region, which is the upper region, This upper region here, I will call it PA, pressure at this region. And then the region at the bottom here, this region here is pressure PB, pressure at bottom region. Flow here is faster, so PA is going to be lower than PB, like this. Okay, so if you have pressure A lower than pressure B, then what happens? You have a difference in pressure, right? Difference in pressure produces what? Difference in pressure produces a force. So just like our previous lesson, we learned about the Archimedes principle. Remember, you put it underwater, right? You put the object underwater. There is a difference pressure between the upper region, point A, and there's a difference in pressure between point B. Which pressure is greater? PB is greater than PA. Because pressure in liquid increases with depth. So PB is greater than PA. Now, what happened because of this effect? A net force is created upward. This is the net force. What do we call this net force? This, we call it upthrust, right? We call this force upthrust. That is the buoyant force from the Archimedes principle. Same thing happened here. Here, you have greater pressure. This is lower pressure. So you will have a net force upward. Net force. But what do we call this net force? You can call it upthrust, but generally we give it a term. We call this the lift. And that is how the lift is produced. That is how the lift is generated. Okay? Based on what principle is this? Based on the Bernoulli's principle. The Bernoulli's principle says that when water or air speed of flow increases, the pressure in that region will decrease. So pressure here decrease, pressure here higher, it will push up here. So a net force will lift up the entire thing. Okay, so it's the same effect we see. Like how the wind blows off the roof of houses. Here you have the houses. When there's a strong wind, the wind blows over the top of the roof. What happened here? You have a high speed of airflow. If you have a high speed of airflow, then it creates a lower pressure region in this area. This area, you have a low pressure region. What happened? Inside the house, where you have a higher pressure region. Inside the house, you have a high pressure region. Up here, above, just the layer of air just above the roof has a low pressure. So high pressure will press, it will push up. So the roof goes on flying. The roof gone. Same thing here. What happened? Same thing as if, okay, like when there's a tornado. Never hide under the bridge when there's a tornado. So let's say there's strong winds. The bridge goes like this. This is the land, and then the bridge like this. During a strong wind, hide anywhere, but don't hide over here. Why? Based on the same thing, same reason. What is the cross-sectional area here? The cross-sectional area here is very small compared to the cross-sectional area here. This is cross-sectional area 1, this is 2. Smaller. Smaller cross-sectional area, what happened to the speed of the air? Continuity A1, B1. Here, if small cross-sectional area, velocity goes very high. So during strong wind, if you hide under the bridge, this will only cause the wind go faster. The wind will go even faster. So you are increasing your chances of being blown away. So please do not do that. Same thing here, right? So when cross-sectional area decrease, the wind goes very high. Everywhere we see the principle of Bernoulli's, we see the principle of continuity of motions. Like the same thing, if you're driving, if you're sitting in a car and then you open the windows, all the things inside the car tend to fly out, right? If you open the windows, because when you go at very high speed, the wind outside blow across the window, right? And then it creates a pressure region, lower pressure region outside. Okay, it creates a lower pressure region outside because the air is moving very fast, right? And then the higher pressure region inside the car pushes everything out. So all the things tends to fly out of the windows. It's because of the same effect here. Okay, the same thing we see when we blow something. Let's say we take a tissue paper or anything. I blow it. I take the tissue paper like this, and I blow it on top. I blow on top. What happened to the tissue paper? Here it creates a low pressure region, and then at the bottom, which is higher pressure region, it will press the tissue paper. What you see is that the tissue paper will rise up like this. It goes from here to here. Even if you blow up, you blow the across the upper region of the tissue, then the tissue goes like this. It raises up. This is also Bernoulli's principle. You have created a lower pressure region. High pressure always push the force to low pressure region. Okay, so that sums up our lesson on the Bernoullis. Now, if the question asks you, for the venturi tube, what happened to the height of the water if the atmospheric pressure is decreased? If atmospheric pressure, TATM, is decreased, what happened to the water height here? Okay, the flow of water going from here to here, we got the height, highest is this one, second, third. If the ATM atmospheric is decreased, that means the pressure preventing it from rising, this one. Okay, this one, if this is decreased, what happened? Logically, you can think if this one, which is preventing the water from coming up, decreases, then the water will rise higher, right? If the atmospheric pressure decreases, then this water will rise higher, even though the pressure here does not change, because the amount of force pressing it decreases. So this one will go up. Okay, so if atmospheric pressure decrease, then what happened? Water level increases. Everybody increases. This one, all together, it will increase. What happens if I use a denser liquid? If I use a denser liquid like this, if density of liquid increases, what happened to the water level here? Now, think of it logically. Density is what? You can think of it like mass over volume, right? Mass, volume. So mass, if density increases, that means this liquid gets heavier. If the density increases, the liquid gets heavier. Heavier, that means what? That means what? Same pressure, the liquid gets heavier, it will decrease. Okay? If the liquid gets heavier, but the pressure doesn't change, then the height of the column will decrease. It cannot push as high as before already because the density has increased, the mass has increased, right? So the pressure here, which is the same, it cannot push as high as before. So that means the height here will decrease, the height here will decrease. So if density increase, water level will decrease. Okay, these are the two typical questions that they will ask. Okay. Now take. Okay, let me check the internet again. Looks like it's slowing down a bit. Okay, I just got disconnected. Let me do a quick test run. Okay, I'll send the exercise in the group. In the meantime, I'll fix the internet. Okay, in the meantime, you can do the exercises from the. Okay, now should be okay. Now it's not very stable. So okay, so this is our lesson on the Bernoulli. So we'll stop here for a second and I'll send the exercises in the group. You try out the exercises and after that we will discuss a few questions on the board. Okay, already sent in the group, so you guys do it. And I go down and see if I go down and take the adapter because I want to use the LAN cable. The Wi-Fi is not very stable, so I want to get the adapter so that I can connect the LAN cable. So I'll be back in a few minutes. Okay, let me see if this works. I will change to my LAN cable. It might be, we might be disconnected. Okay, testing sound. If the sound is okay, very smooth, can you put a 1 in the chat? I'm currently using my LAN cable. If the sound is good, it's smooth, let me know. Put a 1 in the chat. Okay, all right. Okay, any question on the exercise, let me know. Okay, for question 2, for 2A, okay, figure 5 shows ping pong ball that does not fall when water flows through the filter funnel. A1, mark the region where the speed of water flow is highest with the letter K. The speed is the highest with the letter K. Okay, the water flows down. And then it flows to the side, to the side here and here. Okay, where is the fastest, water speed fastest? Over here. This region here is where the speed flow is the fastest, inside. You have two regions, K here and K here. Okay, and the contact point here. If you see how the force is acting at this ball, when the water is flowing, right, this ball is not moving. It stays at rest like this. It doesn't drop because it is supported by a force. What force is that? Okay, we have weight. We have weight. With the weight, it should go down, right? But it doesn't go down because water flowing very fast at here. So it creates a high pressure region in this region. It creates a low pressure region in this one. So there will be a force pressing against it, like this. This force is the force due to the pressure difference. Because this region is low pressure, so this region is high pressure, the force is pushing like this. Why the force should come like this? Because here actually you have a reaction. Here you have a reaction, R. The ball is touching, right? The ball is touching the funnel. So you have a reaction force. The reaction force is always normal to the what? To the boundary, right? To this surface. So the reaction force like this. That means your force must be coming from this direction. Same happened here. There's a reaction like this. So you have a force pushing from here. F. Okay, these two forces are due to the pressure difference. You can call this upthrust, whatever you want to call it. I'll just call it F1, F2. These two forces are the forces that keeps the weight, okay, are the two forces that balances out the weight here. Okay, so that is the for question 2. Speed fastest is here, okay, in between the what? In between the funnel and the ping pong ball. In between the funnel, not here at the middle, because when the speed goes down, it hit the ball here. There is a static point at here. So water should be faster, higher velocity over here. Okay, so explain how the force is created. So air pressure below the ping pong ball. Okay, that's for number 2.